First paper will be presented by Gong, who unfortunately cannot be here because of visa reasons. We recorded a video of his talk, so we present that, and then we will Skype him in for questions.
That's
right?
cool. Yep.
Yeah. So the talk is on instrumenting and analyzing fabrication activities, users, and expertise done in collaboration with Autodesk Research and Dartmouth College.
Right. Thanks, Ross. Yeah, I really wanted June to be able to be in front of this work because he put a tremendous amount of work into the system. So without further ado, here's June.
Hello everyone, my name is Gong. I'm a fourth-year PhD student from X Discovery Lab at Dartmouth College. Today I'm going to talk about instrumenting and analyzing fabrication activities, users, and expertise. This work was done during my internship at Autodesk Research Toronto, where I was advised by Fraser, George, and Tovi. Nowadays, fabrication and making activities are getting more and more popular within research as well as the general population. A wide range of individuals with wiring abilities, requirements, and skills are coming to the fabrication space to work on their own projects. However, the tools and the environments used in this making process do not sense or adapt to the fabrication context. For example, is this girl following the correct procedure when using this machine? Does this guy need some guidance when soldering? So we envision a monitored, reactive, and adaptive fabrication space that can provide personalized information, feedback, and assistance to the users while they are using the space. A good example would be providing customized tutorials to the users in different expertise levels. To achieve the goal, we explore the sensorization of making and fabrication activities where the environment, tools, and users were considered to be separate entities that could be instrumented for data collection. From the collected data, we are interested in three kinds of contextual information: which users are performing the activities, which activities are being performed, and what expertise the users have. Before I dive in, let me first quickly go into the related work. There is a lot of rich work in investigating sensing and context recognition. Here are several examples. Body-worn sensors like microphones and accelerometers were proved effective to recognize different activities like sawing, drilling within a workshop context. Cameras can always provide rich information, and lots of computer vision algorithms were proposed to detect daily activities. More recently, generalized sensing packages such as synthetic sensors have been used to detect several environmental states through a combination of sensing modalities. Our work builds on this previous work by considering the context of fabrication and analyzing how the user, tools, and the environment can be instrumented to provide different contextual information. And we go beyond identifying what activities is being carried out and try to identify how that activity is being performed and by who. So next, let me talk about the sensing system we built. As fabrication activities are conducted by an individual using a tool within an environment, we explore placing different types of sensors at these three entities. For instrumenting the environment, an accelerometer and a microphone were used. The high-frequency accelerometer can capture vibration signatures while different users were performing different physical tasks. And the audio data can also effectively infer what machinery or appliance are being used in the space. So here is the customized PCB where the accelerometers and microphones were soldered on. The sensors were sampled by a Tinsy microcontroller, transmitting the data to the laptop through serial. For instrumenting the tools, we use a sensor tag from Texas Instruments since it contains a wide variety of sensors, and its compact size and wireless nature would have minimum effect on users' operation. This small wireless sensor package contains a 9-axis IMU as well as ambient light, humidity, temperature, pressure, and a magnet sensor. For our purposes, we only used 9-axis IMU, including accelerometer, gyrometer, magnetometer to track the tool's orientation and vibration, which we believe could be good indicators of users' expertise level. Ambient light sensor was also used for a similar purpose. The sensor tag connected to an iPhone through Bluetooth Low Energy, transmitting all the data back to the laptop through Wi-Fi. For instrumenting the users, the primary consideration is unobtrusiveness and having minimum effect on users' operation. So we used off-the-shelf wearable devices to capture users' data. Each user was instrumented with an eye tracker, which recorded gaze position. For the gaze position data, we are interested in whether the user is looking at a fixed point. So we calculate the number of saccades within a time window. Each person was also outfitted with 2 Apple Watches, one on each wrist. The watches recorded the movement of hands via accelerometers and gyrometers. The heart rate was also recorded, which may indicate the user's confidence while performing the tasks. The smartwatches were each connected to an iPhone, running an application which reads the data from the sensor and relays that to the laptop through Wi-Fi. So here is the system overview. In summary, we explore 4 different types of data: motion, audio, ambient environment, and biometrics. We distribute all the corresponding sensors on 3 entities: users, tools, and environment. So here is a short video demo showing all the sensor data are streaming into the laptop simultaneously. The laptop screen shows the spectrogram of different sensor data. Armed with this sensing system, we conducted a study to collect data for representative fabrication tasks. We recruited 14 participants with a broad range of expertise in physical tasks through a pre-screening questionnaire. We selected the participants based on their self-assessed expertise to maximize the range of skills that the participants had. We deployed a sensing system and collected data in an active workshop containing a number of 3D printers, a CNC machine, and lots of electronic equipment. While the data was being collected, the rest of the workshop was open to its users, and other tools and equipment were in use. 2 video cameras captured the video and audio of the tasks for the later review. Each participant was asked to perform 7 representative physical tasks. Use the deburring tool to clean the inside edge of a roughly cut aluminum pipe. Hammer a nail into a piece of wood. Use a hand drill to screw into a piece of wood. Use the handsaw to make a straight and a clean cut at a piece of wood. Drill a hole through a piece of acrylic. Solder separate mile headers on a general-purpose PCB. Send a piece of wood to the marked contour with a spindle sander and a drill press. For each task, participants perform 2 blocks, each of 4 trials. Between the 2 blocks, participants watched an instructional video which contained a tutorial on how to perform that task. This experimental design was intended to allow the capture of a wider range of behaviors from novice to more expert. So here's an instructional video example for drilling.
Make sure the drill is perfectly upright. We don't want it at any angle. And light pressure as we drill, keeping it cool. Once we can see wood chips coming up, we know that we've gone all the way through. Keep the drill moving as you pull it out. And we can clean the chips off. And we have a nice clean hole.
After collecting the raw data, we start to explore higher level contextual information that can be obtained from this data. Let me first talk about the featureization and the machine learning pipeline in more detail. So first of all, the raw sensing data including motion, audio, ambient environment, and biometrics are coming from 3 instrumented entities: environment, user, and tool. And then we perform featureization on this raw data. We calculate FFTs and 7 statistical features, including max, mean, sum, standard deviation, and so on and so forth. After the feature vector is packed, we fit it into a random forest model to extract 3 elements of contextual information: identification of which user is performing the task, which task the user is performing, and what expertise the user has. Besides the accuracy, we also aim to build an understanding of how different sensors in different locations can contribute to identifying this information. Next, let me briefly talk about the data analysis results for user identification, activity recognition, and expertise inference, and 3 takeaways from the results. So for user identification, in order to overcome the possible strong correlation in data samples due to the high sampling rate, we calculate the accuracy using a leave one block out approach. For each task, we train the model using the data from one block and test it using the data from the other block. The figure shows the average accuracy of 7 tasks using the sensing data from different entities. So the overall average accuracy across all 7 tasks with all sensor data was 93.8%. And as expected, the average accuracy dropped when only using the sensing data from the environment, tools, and the users. From the figure, we can see that environmental sensors perform much better than the user-own sensors in user identification. We assume it is because environmental sensors have much higher sampling rate than the sensors on the users, so that environmental sensors can capture the tool's interactions with the material. But the unique individual movements of the rest are not captured by the user-own sensors. After looking into the results for each physical task, we find several interesting patterns. First, Neuralink achieved the most balanced performance using these 3 types of data, which means that we could capture meaningful information from all 3 data sources in order to identify which user is hammering. Second, sending achieved the lowest accuracy with all sensor data available, which may be due to similar sending operation behaviors among all participants. As for activity recognition, we tested whether the machine learning model worked well across different users. So we used the data from 13 participants for training and the remaining participants for testing. Same here, the figure shows the average accuracy of 7 tasks using the sensing data from different entities. The overall average accuracy with all sensor data was 94.2%. And as expected, sensors on the tools contribute the most on activity recognition since the unique vibration patterns or operation movements can be easily captured by the IMU on the tools. Here is the confusion matrix for 7 physical tasks. We can see that it was difficult to clearly distinguish between screwing and drilling since these 2 tasks use the same tool and had a similar procedure to operate. Finally, for expertise inference, we asked 2 experts to watch the video clips of the participants performing the tasks and rated them from 1 to 7 for each trial. We used the mean ratings as our ground truth. Since we want to obtain a continuous evaluation score of users' expertise, we use random forest regressor instead as the model for expertise inference. For each task, we use the data from 13 participants for training and then infer the expertise on the remaining participant. We evaluate the results using root mean square error. Here's the figure showing the results using different sensing data. The overall average root mean square error with all sensor data was 1.27. Please note that the root mean square error between 2 expert ratings across all trials was 1.37, indicating that expertise evaluation is somewhat subjective, but our approach performs very similar to the human evaluator. You may be wondering why this will work. Let me just quickly show you an example of deburring. On your left-hand side is the novice user trying to deburr the pipe, and on your right-hand side is the expert. We can easily find out 2 different movement patterns between the novice and expert, which can also be seen from the motion sensors, microphone, even light sensors in our sensing system. Due to the time limit, I won't be able to discuss too many details about how different sensors in different locations can contribute to identifying what kind of contextual information. Please refer to our paper for more discussions. But here, I want to share 3 takeaways with you. Through the instrumentation of environment, tools, and users, our system can recognize the activities and the users with high accuracy and can infer the expertise of the user at a similar level as human readers. Environmental sensors contribute the most in user identification and expertise inference. Sensors on the tools contribute most in activity recognition. That's all for the data analysis. Next, let's see what could happen if we have this contextual information. As shown in this video, after detecting a novice user is operating a drill, a responsive environment could lock him out of accessing more dangerous tools or equipment. By having a historical view of activities in the workshop manager can make more intelligent decisions regarding to planning the space. After detecting a user's skill level, the system can suggest more expertise-appropriate tutorials, helping novice to become more confident or giving a skilled user some expert hints. That's for the sample use cases. Next, I will discuss the future work. We try to recruit participants in a wide range of expertise in different tasks, but the expertise with different tasks is not completely balanced, and the nature of expertise is quite subjective. More work is needed to determine more objective measures of expertise that can be used as a baseline. Although the studied test did have some complexity and varied stages, the tasks were still simplified and controlled. More work is needed to ensure the system still works as the environment, orientation, or the materials used in the tasks are changed. Further, we are also interested in detecting multiple activities and users simultaneously, which might need a thorough evaluation. Users would change their behaviors while getting more experience and expertise, which may affect the user's identification. A long-term study in this field is necessary for the future work. That's all I want to share about for today, and I'm more than happy to take any questions.
Are you there, June?
Okay, let's try to Skype in Gong, and
Can you hear June?
we can line up for questions in the meantime.
Shall I ask you now?
June, are you there? Okay, June is here. I may have to repeat the question.
Fantastic. So this is Andrea from KAIST. I would like to know a little bit more about the limitation of supervised learning here. So obviously, when you saw there are different kind of components, different type of ICs, when you say drill different kind of material, when you cut something in a different shape, well, the supervised training might not actually hold anymore. Can you actually elaborate a little bit about the limitation of this work?
Did you catch all that, June?
With my nice voice.
Yeah. You just don't want to answer hard questions?
I can't hear clearly, so could you repeat that question for me?
How do you deal with changes in material or context with supervised learning? So when you drill on a piece of material that you haven't trained with the system.
Wow. So it's a lot question actually. So we would try. So in the study we conducted, so we fixed the material and we fixed the tools that we need to use. It needs more exploration on how to apply this model to the more diverse materials and orientations and.
So in short, he agrees it's a hard problem, and I think it'll require future work. And as we get more data, and if we can deploy, the sensors are getting cheaper, we can deploy them on construction sites and in fabrication spaces that have that diversity of materials, and then throw it up on Mechanical Turk to get that supervised labeling.
Okay. Yeah. So, one more question. Yeah.
So I'm really fascinated by the expertise learning here, and I'm wondering about the ability to then turn around and learn expert behaviors from the experts and then kind of have a continual learning cycle.
So Jude, he's asking about how we could use the detected expertise to sort of train the next novice user and use it as a teaching task. Have you thought about that? All right, this isn't going to work. But I think it's super useful and a good idea. I think you need the experts initially to start tagging that, but if you can start to identify expert behaviors, then you can maybe start to capture different contexts of use. So you maybe have, your one expert, but then you have other recognized experts that are doing something a little bit different, and you can start to use them as learners for maybe peers or for the next generation, so you're not just learning from that one expert.
Great. Okay, let's thank
you guys.
Gong again.
Thank you.